Today, 80 Chem fans. Today we're going to be taking a look at these things called titrations, which are pretty darn handy, and how we can use those to figure out the equivalence point. Think about equiv, sounds like equal, right? And how do you determine the strength of an acid or a base? Well, they're all kind of connected together. So these little monsters will tell you that there are some tricks to figuring this out, of course, and one of those tricks I gave you last class, there's some things to remember. If you're figuring out things with acids and talk about pH and you need a P, you P on a log, right? So if you need the pH, you'll log it, right? The negative log will provide that for you. If, however, you don't need the P, that means that you probably already have the pH. You can use that to figure out just the H. So if you don't need the P, then you can use that P as a power. That's to the negative power of the exponent for the pH. You just use that, put that on a 10, use that as a power, and that will then give you the hydrogen ion concentration. The cool thing is if you figure out those two tricks, if you're trying to figure out stuff for OHs or POHs, it's the same tricks. If you need a P, P on a log. If you got a P, use it as a power. That's how I keep track of it. Another tool that some people use that's pretty effective for them, you can use it if you want, is this one. First, I'm going to show it to you. You're going to write it down. Pause me right now so you can write down the diagram. It looks kind of fancy and complex, but then think about how it actually works. So pause me. Now I'm going to explain it like I normally would with you in class. If we look at this, we can see that we have this thing called pH and POH. You can see that the combination of those two, the addition of them, is exactly 14.0. That's why it's a 14.0 scale. If we look at the P, if I need a P, then I use a log, which is what this is showing. A negative log of the hydrogen ion concentration will give me the pH. If I've got the P, I can use that in the place of this X to figure out the hydrogen concentration. I can power it. Likewise, I can do that with the POH. If I need to pee, I pee on a negative log because it's not very polite to pee in public on logs, right? So that, of course, would give me the pH. If I have the P, I would use that as 10 to the negative POH to give me the hydroxide ion concentration. Works great. Then you can see the most important part of this is if we look at the hydrogen and the hydroxide concentrations, when you multiply them together, you will get exactly 1 times 10 to the negative 14th. That's why the scale is based on 14, because it's really talking about the power of the exponent. So hopefully you notice that exponents are pretty important when we're talking about things like pH. This is a handy tool that some people draw on their final test for the year. It's definitely helpful when you go off to college or you're going to face pH throughout the rest of your life because, the environment's becoming acidic. And it's a lot of science that's tied to it, like your blood chemistry. Now, today what we're going to take a look at is fish tanks, right? A miniature ocean, and another solution that's got this POH thing. So pause me, write down the questions, then we'll try to solve them together. I'll get rid of my big ugly head, as usual. Boom, there he disappears. Much prettier. Cool, let's take this on together. ETD 80. Crazy, right? So, as with all problems this year, it's about figuring out what you got and what you need. And recognize that usually when you're running into things like pH and POH questions, it's going to take at least 2 steps to follow them. So figure out the 2 steps. You can take multiple steps to solve them, but it's 2 steps usually to solve them. So what do I need, right? It wants to know what the hydrogen ion concentration. That's what I'm looking for at the end of this thing, right? And then, of course, it's asking in there, with that, it's giving me the POH. So I've got a POH of 6.42. Okay, well, I got a P, so I don't need a log, right? So here's how I would solve this, though you can solve them in many ways. First thing I know is I need to get to the hydrogen ion concentration, so I'm going to use this POH to get to the hydroxide ion concentration because those two things come together to make HOH, water, right? Since I've got a P, I'm going to use it as a power. That's 10 to the negative POH, right? So then I can just take that and plug it in. That's 10 to the negative 6.42. My calculator does my heavy lifting for me. And when I pop it out the other side, it tells me the hydroxide ion concentration is 3.80 times 10 to the negative 7 moles per liter of hydroxide. Notice I'm writing the units now, right? Now, we're using 3 siggy figgies to make things easier. Be aware with pH and POH, there's a slightly different sig fig rule that you might run into in college, but we're going to keep it simple so your heads don't explode, right? Now, the other part of this, of course, is now I've got the hydroxide ion concentration. I don't want that. I want the hydrogen ion concentration, but that's okay. They're both tied together in this thing called water. KW. The W is for water. In just plain water, there's, of course, a constant that we come up with. The hydrogen ion concentration times the hydroxide ion concentration is always equal to 1 times 10 to the negative 14th. It's 1.0 times 10 to the negative 14th. That's why the scale's out of 14, right? Because that, of course, would mean that there's times 10 to the negative 7 H's and times 10 to the negative 7 OH's to make, when you factor them together, to the negative 14th. Right? Now I can use this because I know some of these things. I know that it should come out to 1 times 10 to the negative 14th. And I don't know what the hydrogen ion concentration is, so that's my unknown. But I just figured out my hydroxide concentration, which is 3.80 times 10 to the negative 7 moles per liter of the hydroxide. And I don't even have to write it because of the brackets, but that's okay, right? If we look at this, then if I solve for the hydrogen ion concentration, my calculator tells me with 3 siggy figgies, it's 2.63 times 10 to the negative 8, because you can use this 1.0 as like an ultimate accurate like moles, right? So it's our question that gives us the siggies, and we started with 3. So when I look at that, of course, that is going to be moles per liter of the hydrogen ion concentrations. And before I box this thing up, I should ask myself if it makes sense. Well, how do you decide if it makes sense? The easiest way to do that is to look at the exponent. That is a negative 8, right? And this is a hydrogen ion concentration. Now, one thing I know is water, pure water, has an ion concentration of 10 to the negative 7. So that is actually a little bit smaller than negative 7, which means this is one extra 0 in front of it, making it a tiny number of the number of hydrogens that are there. Well, less hydrogens means it's less acidic. It's going to be more basic. That would make it a little bit basic because, of course, it's a negative 8. And that's crucial because if I look back at this, this is the pOH scale, which you hopefully remember is the reverse. And anything below 7 on the pOH scale is basic in its nature. If I switch to the pH, it would be the opposite, right? So the numbers do match up, and that negative 8 in hydrogen concentration tells me there's a little less hydrogen, so it's a little more basic. There's a little more hydroxides in there, right? Cool. Always look at the exponents because they're the dead giveaway. If we look at the other one, right? Okay, what do I got? What do I need, right? What I got is I got this. I've got the hydrogen ion concentration, and what I need is the pOH. Now, I could tackle this in multiple ways. This is how I'm going to do it. I need to, of course, get to the P's, so I'm going to use my hydrogens to get that. I need a P. I'm going to P on a log, the negative log of the hydrogen ion concentration, right? Cool, I've got those numbers, so I can just plug it in. The negative log of 5.32 times 10 to the negative 3rd. This is when we wish we were in class so that we could actually take a look at your calculator if you're having trouble with figuring out your logs, and then makes your life easier after that. When you plug that in, that'll give you a pH of about 2.27 when you get siggy with it. We're just going to use the simple rules of 3. It's not completely accurate, but we're just going to use it now, right? Now, if we look at this, okay, I've got a pH, but I don't want that. I want the pOH. Well, good news. The pH plus the pOH is exactly equal to 14.00, right? Oh, so this is like easy math. I take my 14.00, pH I just plugged in, 2.27. I add that to the pOH, I subtract it from the other side, and I get a pOH of 11.73. Notice how it usually takes at least 2 steps to solve any one of these problems. Get used to that, right? Now, before I box that up and submit it to Neil, I would ask myself, does that make sense? Well, how do I decide that? I look up here at what they gave me. They just gave me a hydrogen ion concentration that's negative 3. Now, remember, negative 7 is in the neutral category. That's why 7 is, right? So negative 3, that's a big number. That's less zeros in front of it. So these are all small numbers, but that's a relatively large little number, which means that this has got a lot of hydrogens. It's acidic. So the negative 7 would be medium. It'd be neutral, right? So it should be an acidic pOH. And if I look at this, hey, look at that. This is a pretty high pOH because, of course, anything above 7 is acidic. And that is getting close to 14. So that's a pretty high pOH, which is acidic because it's the opposite scale. So don't have your pH and pOH scales mixed up. Don't go cross-eyed on those. Of course, you can always clear that up when you solve it again and think about the exponents. I always just look at the exponents because they tell you how big the number is. And remember here, negative 7 is in the middle. So anything less than negative 7 is a big number. Anything greater than negative 7, like negative 11, is a pretty small number, right? Or zeros in front of it. Scientific notation. Handy stuff. Now, normally we go in after the pH PHET scale thing. We'd look at a TLW and do some textbook stuff. With remote learning, you got less stuff to do, you lucky ducks, but we're going to get out our notes. What we need to look at today are these things called titration curves. And with titration, of course, titration is all about taking a known and mixing it with an unknown. In this case, you can see there's this thing called a burette. It's got this graduations on it. It's highly accurate measuring volume. It's got a base in it that we know the concentration of, and the stopcock controls it so they'll be dripping in, drip, drip, drip by drip. And that would mix with the acid. So these are my OHs, and I'm dropping them into my H's, and I'm neutralizing them to make HOH, water. That's what titration is all about, is getting to neutralizing them, right? So if we look at this, I need to find out the concentration of the H's in here, my acid. So Here's how it works. We use titration curves to measure the volume of a solution of a known concentration. In this case, it's a base. It could be the acid and flipping around the other way. That's called the titrant because you're titrating it. And I'm analyzing this solution. That's why it's called the analyte. Very creative, right? In this case, it's my acid that I want to know the concentration of. When I'm doing that, we'd be doing lab 23. The titrant would be the base in the burette called sodium hydroxide. Our acid would be hydrochloric in the bottom, the acid of the beaker. Or it could be different acids because in lab 23, we're trying weak and strong acids. So it could be some ammonia up here and it could be some acetic down here. Either way, the base is going to be up top for lab 23. The titrant added to the analyte is added to the analyte until the solution has reached this magical point called the equivalence point, which I've hinted at right here. It's when the H's and the OH's match up to make HOH titration. HOH. Yeah, another solid gold hit. Now, if we look at this, the equivalence point, the name kind of gives you away, should make you think of equilibrium. Well, this is kind of tied into that. We usually represent it with a graph, and you should draw this graph. You pause it if you have to, right? And it will always show this snake-like, well, this beautiful S curve, right? Here you can see that the pH is measuring the actual pH of the solution that's below it. In this case, it's below 7, so that's an acidic solution. And then you can see it goes from being an acid. As I'm adding base to it, it becomes basic, and it ends basic. But what really matters is this magical point right here called the equivalence point. The equivalence point is where the number of piles of hydrogen ions matches the piles of hydroxide ions. So this is where moles come in handy. They never go away, those handy moles, right? No wonder we sing about them. So really, the number of H's matches the OH's to make HOH. They're equivalent to each other. Whoa. Now, be aware it's not always going to be 7. On this graph, it is. That's because there's different combinations of strong and weak acids and bases, which is what our lab's about. It's always going to be in the middle of the most vertical jump in the pH. When it goes from acidic to basic, you can see this is, right in the middle, which is a pretty good sign that this was a combination of, well, basically, we can see we had a strong acid and a strong base. So they match up a really good quarterback with a really good receiver, and they cancel out all those H's with OH's. It makes it perfectly HOH, right? Cool. In our lab today, what we'd normally be doing is we're looking at strong and weak acids. We've got some 0.1 molar hydrochloric, some acetic, some sodium hydroxide, and some ammonia. These are my bases. These are my acids. That's a strong one. That's a weak one, right? Good quarterback, weak quarterback. This, of course, is a great receiver, a strong base, sodium hydroxide. You can use in drain cleaner, and a relatively weak base, ammonia, right? We'd add water to those to help dilute them down and make the collisions easier. Each of your partners would take a job, one stirring, one running the stock cock to actually control the flow of those things, and the other watching the computer. But hey, we're virtual today. You'd be mixing 8 milliliters of hydrochloric, the acetic, the hydrochloric, and the acetic with different bases. So you got a strong with a strong, a weak with a strong with a weak, and a weak with a weak. Think about it in terms of quarterback and receivers, in terms of the matchup of those, and you kind of understand the problem that you have sometimes in Seattle. I know Seahawks jokes. You'd be dropping at one drop per second as you get to the highest jump. But for this lab, you can really just dribble it in there, and the computer will do all the work for you. But the best thing to do, of course, is as you get to that vertical point, slow down the rate of it so it's drip, 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 drip. And that, of course, would take you from acid land to base land. At the point where the H's and the OH's match up, you got enough quarterbacks and receivers, you'll get your equivalence point. Pretty simple stuff, right? Today's target was to make sure that we can understand what a titration is. That's where you add an acid to a base, or in this case, a base to an acid, right? To find out the concentration of the unknown acid. In this, or the unknown analyte, which could be an acid or a base, for our lab, it will always be the acid that's being mixed with the base. And we're not actually doing a full titration. We're just finding the equivalence point. The equivalence point is where the H's of all these guys match up with the OH's, so you make HOH. It's pretty straightforward. That's going to change depending on if you have a good quarterback, a strong acid, or a weak quarterback, a weak acid, matched up with a good receiver like sodium hydroxide, a strong receiver, a good base, a strong base, or a weak base like ammonia. Think about who's going to throw the ball and who's going to catch it and how many people are going to fumble and drop the ball back out. That could affect the pH, which we'll talk about more in the next entry test, right? So hopefully you noticed our target was to hit these ideas of titration, adding an acid and a base together to find the equivalence point where the H's and OH's match up. And that can allow you to determine the strength of the acid or base. Just looking at the curves and the pH will give that away, because pH is a pretty handy way to measure it. That's why scientists keep talking about the pH of the ocean.